Another problem I want to look at would be one more maybe. $30. Okay, and what would this be? Well, this is 4. The cosine of pi over 2 is 0. Sine is 1. And this is nothing more than 4i. And there it is. Now, something that's going to allow us, instead of memorizing those formulas of multiplying and dividing, which is the majority of the section or what this is used for, let's backtrack a bit and see how things work. If I called Z1, if Z sub 1 is R sub 1 times e to the I times theta 1, like 3 e to the pi over 2 theta. And if Z2 equal R sub 2 e to the I theta 2. Now, the power of using those, using Demoiver's theorem, if I take Z1 and multiply that by Z2, wouldn't that be R sub 1 e to the I theta 1 times R sub 2 e to the I theta 2? And notice what happens. This becomes R sub 1 times R sub 2 e. When I multiply exponentials, I simply add the powers. And that would be R1 R sub 2 times e. And if I factor an I out, it's simply adding the angles. I'll show you what that means underneath right here in a minute. And add to that, if I take Z1 or Z sub 1 and I divide that by Z sub 2, I will get R sub 1 e to the I theta 1 divided by R sub 2 e to the I theta 2. And that would simply mean I'm getting R sub 1 divided by R sub 2, which is a number, e. And wouldn't you take the top power and subtract the bottom power? This is by the rule of exponentials or exponents. And if you factor an I out, that would be theta 1 minus theta 2. And lastly, and that's one of the most crucial applications, if I take x plus iy and raise that to the n power, we know from the binomial theorem or Pascal's triangle what this would be. If I write this as r e to the I theta, or actually if I write it as r times the cosine of theta plus r times the sine of theta times I, and I write it using using Euler's formula, wouldn't that be r to the n times e? And when you raise powers, don't you just multiply those? So here, I will get r sub 1 times r sub 2, the cosine of theta 1 plus theta 2, plus I, the sine of theta 1 plus theta 2. Here I'll subtract them, and here I'll get r sub n times the cosine of n theta plus I, the sine of n theta. Actually, this is Demoiver's theorem. Now I'd like to look at some problems. Directions. Given two complex numbers, z and w, find z times w and z divided by w. first set of problems they given to us in the polar form. So what we'll do, we'll say this is actually e to the 120 degrees I, and this is e to the 100 degree I. This will make your life a lot easier. If you just write them this way, then the work is going to be really minimal. When you say what is z times w, well, that's e to the 120 degrees I times e to the 100 degree I. And when you multiply exponential functions, remember a to the x times a to the y, that is a to the x plus y. That will be e, and you would simply add those powers. You would simply say that is 120 degrees I plus 100 degree I, which is e to the 220 degree. And since they said leave your answer in polar form, that's pretty much it. And can you guess when we divide those what we will get? That will be e to the 120 degrees I divided by e to the 100 degree I. So what happens if I take a to the x divided by a to the y? Isn't that a to the x divided minus y? And that will be 120 degrees I minus 100 degree I. And that will be e to the 20i, which is the cosine of 20 degrees plus I the sine of 20 degrees. And that's pretty much how things work. And if I take another problem, but that doesn't look like that quite, it's slightly different actually. If I look at a problem like number 42, and this is normally how things look in applications. Those could vary from different applications. You could apply those differently. So if I take this z and I go on the side and I figure out that for z, I'm looking at 1, negative 1. I know r equal radical 2. And this is a reference angle of 45 degrees. That would be what? Pi over 4, or what is it? 45 degrees in the fourth quadrant, right? That would be the equivalent of 315 degrees I. And if I take w and look at how w look like, w would be 1 minus radical 3. Again, a reference angle, r is actually 2 in this case, and I have a reference angle of, this was 45 degrees, and here I'll have a reference angle of 60 degrees, so this is 300 degrees. So pretty much when I say what is z times w, I'd say that's radical 2 e to the 315 degrees I times 2 e to the 300 degrees I. That is 2 radical 2 e, and if I add those powers, that's 615 degrees I. Keep in mind they insist in complex land that this is between 0 and 360 degrees, so I'll take 615 minus 360, and that will be 255 degrees I. And if I take z divided by w, well, z is radical 2 e to the 315 degrees I. W is 2 e to the 300 degrees I, and that would be radical 2 over 2 e to the 15 degrees I. And that's how it works. And if I take the power function, which is a crucial application, I'll show you what that means. So if I take, and I want to do 2 of those as well, oops. Write in standard form, a plus bi. And here they're trying to prove a point to you. Now, this is this one special component of Demoiver's writing this as R to the. So this is a special case of Demoiver's theorem. If I want to apply Demoiver's theorem, that will be 3 cubed times the cosine of 3 times plus I the sine of 3 times. So instead of memorizing that formula, we could say, you know what? According to Euler's formula, this is e to the 80 degrees I cubed. Well, don't you distribute the 3n? And when you raise powers, don't you multiply? And look how simple that looks. And if they say leave it in polar form, there's the answer. But they said write it in a plus bi. So that would be, and then you could write it this way and say that's 3 to the third is 27 times the cosine of 240 degrees. That's a reference angle of 60 degrees. So that is 1/2 plus I times the radical 3 over 2. And 240 degrees, in this quadrant, both of those are negative. So that is negative 27 over 2 minus 27 radical 3 over 2i. And this is such an important property. They gave it a name. They call this Demoiver's theorem. It turns out to be a special case of Euler's if you just write it using Euler formula. I'm going to take number 46, and I'm going to alter that problem slightly. So you might be thinking, you know what, but I could multiply this by itself 3 times. Meaning, if I take this, and I take 3 to the third, if I take cosine of 80 degrees plus I the sine of 80 degrees, and cube that, saying that's a plus bi cubed, and work the cubes out, I should get the same answer. But notice what happened if I alter this problem. If I make this, instead of 4, I'll make it 1600. So if I want to take a plus bi raised to the 1600, you could multiply this by itself 1600 times. That's a lot of times. Or I could say, you know what? This is nothing more than radical 2 times a cos times e to the 5 pi over 16, all raised to the 1600. That will be, well, this is 2 to the 1/2, so that's 2 to the 800 times e. And when you multiply those powers, wouldn't 16 divide 1600 1,000 times? That will be 5,000 pi I. And hey, don't we know where 5,000 pi I is? Isn't it right there? Isn't that 2 to the 800 times the cosine of 5,000 pi plus I the sine of 5,000 pi? That is 2 to the 800. Isn't that a negative 1? And that's a 0. And that turns out to be 5,000. I'm sorry, 5,000 pi is right here. Even, right? 0 pi, 2 pi, 4 pi, 6 pi. Any multiple of pi will be there, integer multiple, so that's a positive. That will be 2 to the 2800. So instead of multiplying this by itself, instead of taking a plus bi and multiplying that by itself 1600 times, guess what? I am going to do a couple more like this, Now, if you might be thinking, why would you want to do that? Can you think of something that runs at like 1600 rounds per minute? Yeah? Ever heard of a thing called RPM? I'll talk about that in the next session.